Hello everyone. Now in the previous couple of videos we introduced the topic of vectors. So what exactly is a vector, how to find the dot product of two vectors and so on. Now we will introduce the topic of matrices and we will do so specifically for two dimensions. So matrices in two dimensions. In further videos we will take a look at matrices in three dimensions, but for now we will look at two dimensions. So first thing we should ask ourselves is what exactly is a matrix? And to understand what a matrix is, we can first consider a system of linear equations. So let's first consider a system of linear equations. So let's say we have 2x plus 5y, which is equal to 1, and we have minus 3x minus 4y, which is equal to minus 5, right? So we have this system of linear equations. Now, what exactly is a system of linear equations? Well, this is just a collection of one or more linear equations that involve the same set of variables. So you can see that both of these linear equations, they involve the same set of variables, which is x and y, right? So we have a system of linear equations, and we can also express this system using vectors. So we can express the left-hand side using a column vector, where we have the components 2x plus 5y, and the other component minus 3x minus 4y. And this is equal to another column vector, 1 minus 5, right? Now, if you look on the left-hand side, each of these components, these are just linear combinations. So we can say that these are linear combinations of x and y. Now, what does this mean? What does it mean to have a linear combination of x and y? Well, let's say, for example, let's say we have two vectors, v and w, right? So if I have a vector v like this, and another vector from this point, and this is the vector w, right? Then the resultant vector will just be 1v plus 1w, right? This is my resultant vector. Now what I can do is I can also maybe multiply each of these vectors by some scalar constant, right? Some scalar quantity. So I could maybe try and have 2v plus 3w, right? So what am I doing here? I'm scaling each of these vectors by some scalar quantity. So 2v will be, if I start from this point, 2v will be double the size, or double the magnitude of this vector. 3w is, we're just scaling the vector w by a factor of 3. So we will have a vector like this. So this is 3w, right? And the resultant vector will be something like this, right? So this will be 2v plus 3w. So this is 2v, right? So what we're doing is we're scaling each of these vectors by some scalar quantity, and then we're adding them, right? And the resulting vector will just be a linear combination. So let's say the resulting vector is u, right? Then u is just a linear combination of v and w, right? So whenever I can write vectors or some sort of variables like this, if I can write av plus bw, where b and a, these are just scalar quantities. So in this case, whatever I get will be a linear combination of v and w, right? Similarly, if I have x and y, if I write ax plus by, this is a linear combination of x and y, right? So in this case, as you can see, we just have the linear combination of x and y for both of the components of this vector, right? So what I can do is I can express this vector here using some special notation. I can express this as a multiplication of some general vector x, y. So basically, what I can do is, if I have 2x, so let me just rub this out first. If I have 2x plus 5y minus 3x minus 4y, I can express this as the multiplication of this general vector with something like this, where we have 2, 5, minus 3, minus 4. And this is an example of a matrix, right? So this is a 2 by 2 matrix. So this 2 indicates that there are 2 rows, and we have 2 rows. And this 2 indicates that there are 2 columns, right? So we have essentially a 2 by 2 matrix. So what exactly is a matrix? This is just, you can view this as a table of numbers, right? A rectangular array of numbers or some sort of mathematical objects. In this case, we're dealing with numbers, right? Each of these are known as the entries of my matrix, right? So I can have in general some matrix with some 2 by 2 matrix with entries A, B, C, and D. If I multiply it with some column vector like this, then what I will get will be another vector, another column vector, where the components will be a linear combination. So I have A times X plus B times Y. So this is a linear combination of my components of the original vector, right? So linear combinations of X and Y, and then I will have Cx plus Dy, right? So you can see that these are just linear combinations of the components of my original vector, right? And you can view this matrix here, you can view this as actually a function, right? So this matrix can represent a function, right? How so? As you can see, this is taking in a vector as an input. We have this vector as an input, and it's giving us another vector as an output, right? And the components are linear combinations of the components of the original vector, right? So we can essentially say that a matrix can represent a function, right? And this function will have a domain. So the domain of this function will be R2, right? What is R2? This is known as the real coordinate space in 2 dimensions. So we briefly explained what this is in some previous videos. So this is the set of all ordered pairs, right? This is the set of all ordered pairs that are real numbers. Right? Ordered pairs of real numbers. So for example, if I have any vector of 2 dimensions, right, like this, all the x components and y components will be real numbers. And every vector, any vector of 2 dimensions whose components are real numbers will be in this set in R2, right, in the real coordinate space in 2 dimensions. So the domain of a function like this, right, we can say that this matrix represents a function, and the domain of that function will be R2. So the set of all vectors of 2 dimensions, right? So if I have a matrix, let's say I can denote a matrix with this capital letter A. If I have a 2 by 2 matrix where the entries are A11, A12, A21, and A22, so these are entries, and these subscripts are representing the row and column that the entry is on. So in general, if I have an entry like this, A subscript I and J, this I tells us the row that the entry is on, the J is telling us the column that the entry is on. So A12, for example, this is in the first row, second column. This is in the second row, second column, right? And if we go back all the way, you can see that this matrix here, 2, 5, minus 3, and minus 4, what do these entries consist of? These just consist of the coefficients of my linear equations, right? We can say that this is just a coefficient matrix, right? It's just a coefficient matrix. So this matrix just consists of all the coefficients of my x and y variables of the linear equation. So the first column contains the coefficients of my x variables. The second column consists of the coefficients of my y variables, right? So this is my coefficient matrix. And I can also have a zero matrix. Just like I had a zero vector where the components were 0. The zero matrix will be a matrix where all the entries are 0. So this is the case for a 2 by 2 matrix. I can extend this to a 3 by 3 matrix like this, where all the entries are 0. So this is a These are zero matrices, right? And once again, I can represent a column vector. I can also say that this is a matrix, right? This is a 2 by 1 matrix. This is a 2 by 1 matrix. We have 2 rows and 1 column, right? So this can also be a 2 by 1 matrix. So now that we have some understanding of what a matrix is, let's take a look at some examples. Let's say that we have some vector, some 2-dimensional column vector, minus 2, 5. We're multiplying this by some 2 by 2 matrix, which has the entries 3, minus 1, 6, and 3. So what will this give us? We will just have the linear combinations of these two components, right? So we will have 3 times minus 2 plus minus 1 times 5, right? And my second component will be 6 times minus 2 plus 3 times 5, and this will just give me minus 11 and 3. Now we can also take a look at another example. Let's say we have a matrix 0, minus 3, 5, minus 1. This is being multiplied by this column vector, and doing so we will get minus 3, minus 26. So you can verify this for yourself. You can check that we should get this. Try this at home. Now we can only multiply a vector that is in 2 dimensions by a 2 by 2 matrix. So let's say we have a vector of 2 dimensions. We can only multiply this vector by a 2 by 2 matrix like this only if the matrix is to the left, right? And doing so, we will have ax plus by, cx plus dy, right? If instead I had this column vector on the left-hand side and the matrix was on the right-hand side, then this is not defined, right? This is not defined. We cannot do this, right? The matrix must be on the left-hand side. So if we remember from the previous class, we looked at our basis vectors I and j, right? So in this case, I'm representing the basis vectors with a hat like this on top to indicate that they're basis vectors. And we know that the I basis vector has the components 1, 0. The j basis vector has the components 0, 1, right? So now if I consider some arbitrary matrix, 2 by 2 matrix, like this, right? If I have a 2 by 2 matrix, A11, A12, A21, A22, then what do I get if I multiply the I basis vector with this matrix A? So if I have A times I, what do I get? Well, let's find out. We have A11, A12, A21, A22, and this is multiplying our basis vector, which has components 1, 0. So as you can see, if I do this, I will have A11 times 1 plus A12 times 0. And then I will have A21 times 1 plus A22 times 0. These are gone. So the resulting thing that I get is just this column vector, right? So I just get this column vector. And as you can see, this is just the first column of my matrix A, right? If you take a look at the first column of my matrix, you can see that I have A11 and A21, which is exactly what I get if I multiply a matrix, if I multiply this matrix by I, right? And similarly, if I multiply A by J, I will have A11, A12, A21, A22 by 0, 1. And doing so, I have A11 times 0, which is 0, plus A12 times 1, right? And then the second component of this vector will be A21 times 0, so we have 0, plus A22 times 1, so we have A22. So this just gives us a column vector with the entries A12, A22. So we just have this column vector. And as you can see, this is just the second column of my matrix A, right? So as you can see, for my second column, I have this result, right? So whenever I multiply a matrix in general, if I multiply some matrix A by this basis vector, I will just get the first column of the matrix. So this is 2, 1, right? And if I instead multiply the matrix A by the J basis vector, I will get the second column, which is A12, A22. Right, so let's keep that in mind. So now let's take a look at something basic. Let's take a look at something such as matrix addition. So how do we add two matrices? Well, it's exactly as how you would expect. If I have A plus B, where A and B are two matrices, so let's say I have the matrix A, A11, A12, A21, A22, plus another matrix, B11, B12, B21, B22. So these are the entries of my matrix B. All I will have to do is for the entry that I have in the first row and first column, I will just add the corresponding entries of A and B, right? It's as simple as that. I will have A11 plus B11, and then for the next entry, I will have A12 plus B12, A21 plus B21, A22 plus B22, right? I'm just adding my corresponding entries together, and this will give me this resulting matrix. So this will be A plus B.